Okay, so now can you see my screen? Can you see my screen? Let me make sure. Okay, thank you. So let's start today's online lecturing. Okay, so let me quickly review the first part of the session 3.5. That is a change of basis. Okay, so we already know the standard basis for R2 or any other vector space, right? So every two-dimensional vector can be represented as a linear combination of E1 and E2. So any two-dimensional vector x, that would be x1 and x2, and it can be represented as s1 times 1, 0 plus s2 times 0, 1, right? So we say that the scalar s1 and x2 are coordinates of x with respect to the standard basis. Okay. Yeah. So usually when we said a vector x, x1 and x2, if we don't mention specifically, we just talk about this vector is represented as represented based on the standard basis, E1, E2, and so on, right? And actually, we can represent the same vector x based on another basis, for example, y and z, because we already know that not only E1 and E2, we can use another set of linear independent vectors like y and z. We can also span R2 based on y and z, right? So in fact, to construct the vector space R2, we have infinite numbers of bases. Okay, so we can also represent the vector x based on y and z, and assume that when we represent x based on y and z, we can write it down as x is equal to alpha y plus beta z. In this case, we said that alpha and beta is the coordinate vectors of x with respect to the order basis y and z. So we can use another basis to represent the same vector, right? So for example here, if y is 2, 1 and z is 1, 4, y and z are linearly independent. And now we have two linearly independent vectors, so they can form a basis for R2. Okay, so assume we have a vector x. When we represent it with respect to the standard basis, it is represent as 7, 7. And if we represent it as with respect to the y and z, in fact, 7, 7 can be written as the linear combination of 3 times 2, 1 plus 1 times 1, 4. That means 3y plus z. So with respect to the basis yz, the coordinate vector of x is 3, 1. Geometrically, that is looking like this. So x originally, if we represent it with respect to the standard basis, that is 1, 0 and 0, 1. The x is represented as 7, 7. And for the same vector 7, 7, we can represent it with respect to the basis y and z. And here we can see that it can be represented as 3y plus z, 1z. That is the same vector x. Okay? And in fact, we can change the coordinate system. So originally, we may represent a vector x with respect to E1 and E2. And now, we want to represent the same vector x with respect to another basis U1 and U2. So how can we do this kinds of transformation, do this kinds of change in a systematic way, And on the contrary, we can also represent a vector x that is originally represented with respect to u1 and u2. But now we want to find its coordinate vectors with respect to e1 and e2. So how can we do that? So first, assume u1 is looking like 3, 2, and u2 is 1, 1. So at the beginning, we try to represent the u1 and u2 are new basis vectors, okay? And we can represent u1 as 3e1 plus 2e2, right? Because any vector in a two-dimensional space can be represented as a linear combination of the standard basis e1 and e2, right? And we can also represent u2 as 1e1 plus 1e2. So in this case, we want to find how can we represent the vector x as u1 as the linear combination of u1 and u2. So assume we need c1 times u1 plus c2 times u2 to do this combination. And then now we can substitute. Then we can substitute u1 as 3e1 plus 2e2. u2 represent as e1 plus e2. And then we do some rearrangement so that we know that the same vector x can be represented as 3c1 plus c2 times e1 and 2c1 plus c2 times e2, right? So actually we know that x1 is equal to 3c1 plus c2, x2 is 2c1 plus c2. What is this? This is the coordinate vector with respect to the standard basis e1 and e2, right? So now we know this relation, right? And we can write down the relation between x and the c, right? Because x1 is equal to 3c1 plus c2. x2 is equal to 2c1 plus c2. Therefore, the relation between x and the c is this. Just like we pre-multiply the column vector c1, c2 by a matrix 3, 2, 1, 1, right? We can write this relation as this. And if we define this matrix as U, we found that actually the matrix U is actually taking U1 and U2 as the column vector, right? Because 3, 2, what is 3, 2? 3, 2 is U1 and 1, 1 is U2. Therefore, this is U1, this is U2, right? So the relation between x and c is actually x is equal to u times c, right? And remember that the matrix U consists of the column vectors of u1 and u2. And what is u1 and u2? u1 and u2 are new basis vectors, right? And now we know that we define U as the transition matrix from the older basis U1, U2 to the standard basis E1 and E2. Okay, so go back to this equation. What does this equation mean? This means originally we represent the vector x as a combination of C1U1 plus C2U2. So C is equal to C1, C2, right? So this equation looks like we transform the coordinate vector with respect to u1, u2 into the coordinate vector with respect to the standard basis. So this is what this sentence says. U is the transition matrix from the order basis u1, u2 to the standard basis e1, e2. Okay? So the matrix U is this kind of transition matrix. Okay? And because U is non-singular, it is invertible. Therefore, because now we know X is equal to U times C, therefore C is equal to U inverse times X, right? And in fact, the U inverse is the transition matrix from E1, E2 to U1, U2. So the inverse means the transformation from the opposite direction. So originally, U is the transition matrix for transforming U1, U2 to E1, E2. On the other hand, U inverse is the transition matrix from E1, E2 to U1, U2. Right? Okay. And now we have a little question here. Why does U must be non-singular? Why? So you can think about why. Okay? So conceptually, we know that what is U? U consists of U1 and U2 as the column vectors, right? And what is U1 and U2? U1 and U2 are new bases. They are linearly independent, right? So if two-dimensional linear independent column vectors form a matrix, then this matrix must be non-singular. Okay, we have mentioned this property before. Okay, so this is why U must be non-singular. Right? So this is a systematic way for us to transform the coordinate vectors with respect to the standard basis to new basis. Or on the other hand, we can use these kinds of transition matrix to transform the coordinate vector with respect to the order basis U1, U2 to standard basis. Okay? So this is an illustration showing this. Okay? So if we transform with respect to U1, U2 with respect to E1, E2, we rely on the transition matrix U. Okay? So with respect to the U1, U2 basis, we have the coordinate vector C, C1, C2. Okay? And with respect to the standard basis U1, E2, we have the coordinate vectors S1 and X2. And then we know the relation is X is equal to U times C, or C is equal to U inverse times X, right? And for the same vector X, S can be written as C1U1 plus C2U2, or X1E1 plus S2E2. Okay. So let's see some example. Assume U1 and U2 is looking like this, and the X is 7, 4. So without special mention, if we just write down a vector X like this, we mean that 7, 4 is the coordinate vector with respect to the standard basis. Okay? And here in this example, we want to find the coordinate of X with respect to U1 and U2. So we want to transform this coordinate vector from with respect to the standard basis E1 and E2 to the coordinate vector C1 and C2 with respect to U1 and U2, right? So how can we do that? Now, we just form the transition matrix. U is equal to U1 and U2. So that it is 3, 2, 1, 1, right? And now, because we want to find the transition matrix from E1, E2 to U1, U2, which is actually U inverse. So we just find the inverse of the matrix U, and we can calculate it as this, right? Because remember that the matrix U is the transition matrix from U1, U2 to E1, E2. Remember the direction. But right now we want to do this. So we need to take the inverse of the matrix U. After doing that, we can pre-multiply X by the matrix U inverse to get the coordinate vector C1 and C2. That is 3, negative 2, right? So X is equal to C1U1 plus C2U2. That is equal to 3U1 minus 2U2. So you can verify this. You just try to multiply 3, 2 by 3, and then minus 2 times 1, 1. And then you can get 7, 4. So 7, 4 is the original vector here, 7, 4, with respect to the standard basis. Okay? So this is the simple step we need to do to transform, to change the basis, right? Okay. So let's see some other example. Let B1 and B2 as these two vectors, and find the transition matrix from E1, E2 to B1, B2, and determine the coordinate of X with respect to B1, B2. So this example is similar, right? Because we first form the transition matrix from B1, B2 to E1, E2. That is just the column vectors 1, negative 1, negative 2, and 3. And then we take inverse of this matrix, we get 3, 1, and 2, 1. And then we pre-multiply X by B inverse to get C1, C2, so that we can get 7, 3. Therefore, X is 7B1 plus 3B2, right? Okay, that's quite simple. You just need to remember the direction. You transform from which basis to which basis. Okay. So in this part, we want to find we just find the transition matrix with transition matrix from E1, E2 to U1, U2, or from U1, U2 to E1, E2. However, we can generalize this further. Okay, so if now we have two bases. One basis vector consists of V1, V2. Another basis vector is U1, U2. Both of them are not standard basis. Okay, and we assume that if we represent the vector X with respect to V1, V2, the coordinate vector is D1 and D2. If we represent it with respect to U1, U2, then the coordinate vector is C1 and C2, right? So in this case, D1, V1 plus D2, V2 is equal to C1, U1 plus C2, U2. And we want to find the transition matrix S, so that we can transform the coordinate vector D to C. Okay, we want to find these kinds of transition matrix S. How can we do that? Okay, so assume we have a vector x, and its coordinate with respect to v1, v2 is written like c1, v1 plus c2, v2. And if it is written with respect to u1 and u2, the coordinate vector is d1 and d2. Okay, so now we set the first basis is capital V, that is equal to v1 and v2. Another basis is u. No, not this. This should be a matrix. Sorry, the capital V is a matrix, consists of the column vectors v1 and v2, and u is another matrix, consists of the column vector u1 and u2. Okay, so if we define these two matrices, then this equation can be written in matrix form, right? So VC is equal to UD, right? We already know what we are going to do. We want to find the relation between D and C. We want to find the matrix S, okay? And we know the relation between them should be written like this. And now we define the V1 and the V2 to form a matrix capital V. U1 and U2, we form a matrix called capital U. Then we can write the relation in matrix form as VC equals to UD, right? The notation here is different. Sorry, the notation here is different. So you just just look at this. Okay, just look at this. So in this case, VC is equal to UD. Okay, and then D is equal to U inverse VC, right? Correct? Okay, so D can be written as U inverse VC. Okay, so we write it down as this. And let me check if there's anything wrong. C, D with respect to V1, V2. So these two slides would make you confused, because you see here, in this case, in these slides, D1 and D2 is the coordinate vectors with respect to V1, V2. However, in this slides, D1 and D2 is the coordinate vector with respect to U. Okay, so these two slides are bad. Okay, maybe I need to make some modification. But basically, the way we derive the transition matrix should be the same. Okay, should be the same. So please take a look at your textbook carefully if they make these kinds of mistake. Okay, so now we know, just take this. Okay, D is equal to U inverse VC. Okay, thus given the vector x in R2 and its coordinate with coordinate vector C with respect to the order basis V1, V2, and if we want to find the coordinate vectors of x with respect to U1, U2, we simply multiply C by the transition matrix S. That is U inverse V. So just take a look at this equation. What does this equation mean? This means originally we represent a vector with respect to the order basis V. But now we want to transform this coordinate vector into another coordinate vector D that is with respect to the new basis V1 and V2. U1 and U2, and the transition matrix should be U inverse V, okay? So let's take a look at a real example. In this example, we want to find the transition matrix corresponding to the change of basis from V1, V2 to U1, U2. Okay, so now we calculate the matrix S. That is equal to U inverse V. And the V is 5273. 5273. Why? Okay, it should tell us, it just tells us that the V is 5273. Okay. And U is 3211. Find the transition matrix where. What is this? Okay. So basically, it just tells us that V1 and V2 is these two, and according to this matrix U inverse, we can calculate the original U1 and U2. That is looking like 3, 2, and 1, 1. Okay. And VC is equal to X. VC is equal to X, and the U inverse X is equal to D. Okay. So that U inverse VC is equal to D. And the U inverse V is the transition matrix from V1, V2 to U1, U2. Okay. So what does this mean? That means that originally we want to transform the coordinate vector with respect to V1, V2 to U1, U2. And we know that the transition matrix is U inverse V, right? And in fact, we can separate this transition into two parts. The first part is we transform the coordinate vector with respect to V1, V2 to the coordinate vector with respect to standard basis E1 and E2. And we can apply the matrix V, right? And then we can transform E1, E2 to U1, U2. And we can apply the matrix U inverse. So if we do these two steps, that is equal to we do one step, and the corresponding transition matrix is U inverse V. Okay? So we can do that. Okay? So let me explain this part in Chinese again. 好，我这边呢，因为这里这个例子有一点讨厌。好，我们现在在讲的事情是说我们如何做转换基底这件事情。OK， 好，那本来呢，一个向量，比如说74这个向量，它是用标准基底来表达的。那我们想要去找说，当它换成是 U1、U2 当基底的时候，它的坐标向量要变成什么？好，那这里就告诉你一个方法啦。那就是说呢，我就把 U1 跟 U2 呢，我表达成标准基底，啊，那事实上就叫32跟11啦。好，那我就把32跟11呢，我形成一个矩阵 U。这个转换矩阵是从哪里转到哪里呢？这里的重点在于你要记住，这个意义是从谁转到谁啦。你如果单纯只是把 U1、U2 聚在一起变成的这个矩阵，其实它转的就是你从 U1、U2 当基底，转成 E1、E2 当基底。OK， 好，那我们现在的目标是原本是用 E1、E2 当基底的，要变成 U1、U2 当基底啊，那就是反过来。那反过来的转换矩阵会是谁呢？就是你 U 这个基底的反矩阵嘛。好，其实就是这个意思。好，那我们就要更进一步的。那如果说今天我们的转换基底都不是牵涉到标准基底，比如说我原本呢有一个向量是用 V1、V2 来当基底的，我现在要把它转成是 U1、U2 来当基底。好，那这中间应该怎么做？好， 那这一页呢，这是一个示意图啦哈。这里的我刚刚一直有点卡住，就是因为这一页给的例子是它的向量 D 是以 V1、V2 当基底，向量 C 是以 U1、U2 当基底，可是底下这一页的举的例子又是向量 C 是以 V1、V2 当基底，向量 D 是以 U1、U2 当基底啦。好，所以这中间有一点不 match。不过呢，我们就是以第32页这里的这个讲解为基准。好，所以的话，经过这一番推导呢，我们就推导出说，好，你呢要把用 V 当基底的，好，转成用 U 来当基底，你这两个的坐标向量之间的关系是长这个样子。好，所以你如果是要用把 V 当基底变成 U 当基底的，你就是乘上这个 transition matrix。好，那这个 transition matrix 呢，我们给它一个名字叫做 S。好 ，S 呢就等于 U inverse V。好啦，那下面一页呢，这里就会告诉你说啊，其实啊，你现在要从 V 当基底转成 U 当基底，一步到位的方式是，我们就乘上 U inverse V 这个转换矩阵。好，但你如果没有要一步到位，其实你也可以用之前我们在第一趴所讲的，那我就先把本来是用 V 当基底的，变成是标准基底，变成是它去转成是标准基底，然后呢，再从标准基底转成是用 U 来当基底，对不对？分两步嘛。好，那如同刚刚所说的嘛，你把 V 当基底变成以标准基底来当基底，那你中间乘的其实就是你直接把 V1、V2 当成是这个转换矩阵的 column vector， 其实这个就是你要的转换矩阵了。好，反之你要把 E1、E2 转换成 U1、U2， 那你就是要怎么样？你就把 U1 跟 U2 形成一个矩阵，叫做大 U。但是呢，你现在转换的方向是这个方向，所以呢，你就是要去取 U 的 inverse 嘛。好，所以呢，你要从 V 转 U， 你可以先把 V 转成 E， 再把 E 转成 U， 分两步骤，这样子就可以了。好 ，OK， so in this part, the general definition of changeable basis can be written like this. Okay, so that V be a vector space, and the E equal to V1, V2 to Vn would be the order basis for V, capital V. If a vector small v is any element of capital V, then this vector V can be written as a linear combination of V1, V2 to Vn. Okay, and we said that the vector C is the coordinate vector of the vector V with respect to the basis. Okay, so the vector C defined in this way is called the coordinate vector of V, coordinate vectors of V, with respect to the order basis, and is denoted as V and the subscript E in this textbook, in this book. Okay, and the C are called the coordinate of V relative to E or with respect to E. Okay, so let's see another example. Let VE as E1, V1, V2 to V3. Okay, and F is the set of U1, U2, and U3. These two set of vectors form two bases. Okay, and now we want to find the transition matrix from E to F. Okay, so this is the first question. The second question, if a vector X is 3v1 plus 2v2 minus v3, we want to find the coordinate of X with respect to a basis F. So originally, the vector X is written with respect to the basis of E. But now we want to read it as a coordinate with respect to the basis F. Okay, so how can we do that? So remember this relation. We want to transform from V1, V2, V3 to U1, U2, U3, right? So we already remember that the transition matrix between E and F is U inverse V. And in fact, we can transform V1, V2, V3 to E1, E2, E3 first by the transition matrix V. And then we can transform E1, E2, E3 to U1, U2, U3 by the transition matrix U inverse, right? And now we directly calculate U inverse V. So V is 1, 1, 1, 2, 3, 2, 1, 5, 4. Why? Because V1 is 1, 1, 1, 2, 3, 2, 1, 5, 4, right? And U is 1, 1, 0, 1, 2, 0, and 1, 2, 1, right? And we take the inverse. And after calculate the inverse of U, we can calculate this. And then finally, we get the matrix S looking like this. And when we want to find a coordinate vector of X with respect to F, we just pre-multiply 3 to -1 with the matrix S so that we can get 8, -5, 3. And we can do the same thing for the vector Y. We get this, okay? And we can verify this. 8U1 minus 5U2 plus 3U3. That is equal to 3V1 plus 2V2 minus V3, right? So this is the general form of change of basis. Okay? So this is the end of the session 3.5. Any question about this? Any question about session 3.5? Some students say there are some lag, right? 好，有人画面会延迟吗？哦，延迟30秒很久呢。声音会不会延迟？声音没有延迟，那就还好一点。好，画面有时候的确会延迟啊。好，有没有什么问题？好，如果没有的话，我们就休息10分钟再回来咯。好，那我这边先暂停录影。